Hello, let's continue with our lecture. Today we are going to cover a new topic as weather is changing, so we will also change to newer topic. So today we are looking at the ordinary differential equation. We have had some idea of orthonormal functions and related topic, but to have a more general outlook, we need to know little bit about differential equation. We have looked at how a simple differential equation such as a d square y by dx square give rise to Fourier series. If you have a little bit more involved differential equation, then you can have a different orthonormal function and can be used both representing the L2 function as well as various techniques involved solving the ordinary differential equation. Let's continue with our lecture. First, let's start with the ordinary differential equation of order 1. A general first order ordinary differential equation can be written as a dy by dx is equal to f of xy. Here y is a dependent variable and x is a independent variable. This ordinary differential equation can also appear in another form, which is given by p of xy dx plus q of xy dy is equal to 0. They can be transformed from one another without any problem. Can use them in the both forms with the appropriately mapping the p and q and f. One of the easiest method to solve this differential equation is to write in an exact form. For example, suppose we take the differential equation of the form p dx plus q dy, then we essentially write it as a d of phi of xy is equal to 0, where phi of xy is equal to constant represents the solution to the differential equation. In general, we may not be able to write y of x as a f of x, but this function phi of xy generally represents the solution, and sometime we may able to write it in the form f of x is equal to y. Otherwise, we'll have to implicitly assume phi of xy represents the solution. The basic idea here is very similar to what we have done in the complex analysis. We write a p of dx plus q of dy as first derivative, that is a d phi by dx into dx plus d phi by dy into dy. So this essentially is an exact differential, and then now here we identified d phi by dx with the p of xy and d phi by dy with q of xy. This is one of the easiest way of obtaining the solution to the differential equation. Now, in order this equation to be exact differential equation, we need a condition dp by dy is equal to dq by dx, which is essentially saying del square phi by dx into dy is equal to del square phi by dy by dx. That is a ordinary partial differential commute with respect to two variables. Once we have this, we can easily solve this differential equation, and let's do that simple example. Let us look at an example. This is not solved, this is solved. Now the differential equation is given by 1 plus cos y minus cos x plus y into dy minus cos x plus y dx. We can easily identify 1 plus cos y minus cos x plus y to be q of xy, that is coefficient of dy, and then minus cos x plus y with respect to py, which is a coefficient of dx. Once we see that whether it satisfies the condition to be an exact differential equation, that is dq by dx is equal to sine x plus y, and then we also have dp by dy is equal to sine x plus y. These two are essentially same, and it does satisfy the condition for the exact differential equation. So we can solve this. Now we have a function phi of xy, which is given by d phi by dx is equal to p, that is equal to minus cos x plus y. We can easily integrate this, and we get phi of xy is equal to minus sine x plus y plus f of y, because it is a partial differentiation with respect to x. The constant here should be a purely function of a y. Now we have another relation, that is a q is equal to d phi by dy, and here we have a q is equal to 1 minus cos y minus cos x plus y. We can integrate this again and we get the result phi of xy is equal to minus sin x plus y plus sin y plus y into g of x, which is essentially plays the role of constant because of differentiation is a partial differentiation with respect to y. Once we have this two equation, we compare these two solution and then we can identify function g of x and f of y, and from this comparison we get the g of x to be 0 and f of y is equal to sin y plus y. From this we get the general solution to be phi of xy is equal to minus sin x plus y plus sin y plus y is equal to c. So this is essentially represents the solution, that is minus sin x plus y plus sin y plus y is equal to c. We may not be always able to write y as f of x, and in this case we are happy just giving the solution in the form of phi of xy is equal to constant. Let us go ahead and see what happens when the differential equation does not satisfy the condition for exact differential equation, that is dp by dy is equal to dq by dx. We can use a special technique called integrating factor to make the equation exact. Now let's start with the differential equation p dx plus q dy is equal to 0, and here we assume that the differential equation is not exact, that is dp by dy is not equal to dq by dy. Then we can make it exact by multiplying a factor which is called the integrating factor lambda of xy, such that we left and right side of the equation with lambda xy, and then we choose lambda such that the d by dy of lambda into p is equal to d by dx of lambda into q. Once we find out lambda, then it satisfies the condition for exact differential equation, and then we can solve using the same technique which we have used earlier. So this is very interesting method. While you may question whether it is possible to find the integrating factor lambda of xy, it is said that the integrating factor always exists, but there is no general technique or algorithm to determine it. We have been told by mathematicians that the lambda of xy should exist, but we don't know how to get it. We have to find in our own way of how do we find out lambda of xy. The first case is to find out the linear differential equation. That a first order differential equation is said to be linear if it is of the form p into dy by dx plus q into y is equal to f of x. P is only a function of x and q is only a function of x, and there is one term here y, and this is simply dy by dx. It's a first order ordinary differential equation. So we can also write it in the following form: dy by dx is equal to g of x into y is equal to h of x. It is basically by dividing by p of x, we can redefine g of x and h of x, and then we can multiply it by alpha of x on the both sides. So this is to find out integrating factor for the linear first order differential equation. So once we have this, we put the condition on alpha x such that the differential equation is exact, and that condition is d alpha by dx is equal to alpha into g. Now this can be easily integrated and we get an expression for alpha is equal to e power integral g prime of x dx over to x. So this is a way of finding out the integrating factor for a first order linear differential equation. Otherwise we may not have a proper method to figure out the integrating factor. We can check it whether it is an exact or not. D by dx of alpha into y is equal to alpha into dy by dx plus d alpha by dx into y. Now we substitute that from the condition of differential equation given here, and then we get it alpha into dy by dx plus alpha into g into y, and that is equal to alpha into dy by dx plus g of y, that is equal to alpha into h. So this is to show that it is in fact satisfies the linear first order differential equation. So this is the way we solve a first order linear differential equation. Now let's take an example. Solve a differential equation dy by dx plus 1 by x into y is equal to sine x. We see that here g of x is equal to 1 by x, and the integrating factor can be determined. Alpha is equal to e power integral x g prime of x into dx, that is e power integral of 1 by x, that is e power log x, and that is simply becomes x. So in this case x is the integrating factor. Now we can take alpha to be x and then solve the problem. X into dy by dx plus 1 by x into y is equal to x sine x. Then we can simply combine the term. What we get is d of dx, d of x into y by dx is equal to x into sine x. Now this is an exact differential. We can simply integrate it on the both sides. We have exact differentiation that gives you x into y. Aside, what we get is the integration of x sine x taken with the variable x. So this in fact is given as a minus x into cos x plus sin x plus c. So this is integration we have seen can be easily done using integration by parts. We have had this similar function when we did the Fourier series of a function f of x is equal to x. So once we do that, we have the solution y is equal to minus cos x plus 1 by x sin x plus c by x, where c is a constant in this case, and this is how we determine the solution to a linear first order ordinary differential equation. There is a homework problem here. You need to solve first order differential equation dy by dx is equal to minus 4 by x into y is equal to x to the power 5 e power x, and you can upload the solution on the vLearn. Let's go on to second order differential equation. We have already seen that solving the first order differential equation is a rather trivial game, because we have seen that integrating factor can solve the first order differential equation. When we come to second order differential equation, situation might get little complicated, and let's have a look at the form of a second order differential equation. We often look at the differential equation of the form. This is a compact notation for the differential operator in the variable x, and which is operating on the dependent variable y. That is, in this case, we are looking at the differential operator of the form d square y by dx square plus p into dy by dx and q into y is equal to s of x. This coefficient p of x and q of x, p of x and q of x can be in general polynomials of the form p1 of x by p2 of x. That is, it could be ratio of polynomial. There is no need to restrict them in a specific manner. Now s of x, we have already seen, it is called the source function. When source function is 0, then what we have is a homogeneous differential equation. When source function is not 0, then we need to solve it. Specific techniques are, we will look at that little while later. Now let us focus on the homogeneous differential equation. We are interested in the real function. We could also have complex function. However, let's more focus on the real function. To start with, we can assume that p of x and q of x have no singularity on the x-axis. So this is a general idea, that the general second order differential equation with the analytic coefficient p of x and q of x, then we have two linearly independent solutions. Now let us quickly look at some of the way to manipulate this second order differential equation so that we can attempt them to solve. So the first one is called the changing the dependent variable. Let us consider the homogeneous differential equation of the form d square y by dx square plus p of x dy by dx plus q into y is equal to 0. Now we change the dependent variable y of x is equal to capital V of x into capital Y of x. Sometimes it may reduce the differential equation to a specific form such that it can be easily formed. One common way is to change the independent variable x and then reformulate the differential equation in a convenient form. The second way is to change the dependent variable itself so that the differential equation takes the more convenient form. Let y of x be a known function, not necessarily be the solution of this differential equation. So you are basically doing a general transformation. Our goal is to obtain V of x such that we translate differential equation into a differential equation on V of x, which may be easier to solve. Let's first we substitute this into our differential equation given by equation A. Dy by dx is equal to y prime, that is equal to v prime into capital Y plus v into capital Y prime. Now differential equation is a second order, so we need to take a second order differentiation of a variable y. So we get a v double prime into y plus 2 into v prime into capital Y prime plus v of x into capital Y double prime. So this is essentially differentiating the product twice, and we substitute back, and then we get a rather messy differential equation coming out to be v double prime y v double prime capital Y plus 2 into v prime capital Y prime plus v into capital Y double prime. Now we get the second term, which is a p v prime into capital Y and p v into capital Y prime, and then we have a term without any differentiation, that is a q into v into y. So once we have this, we can divide the entire equation by capital Y of x. This function is known to us. Now we combine all the terms. We get v double prime plus 2 capital Y prime by y plus p v prime plus capital Y double prime p into capital Y prime plus q into y divided by y into v of x is equal to 0. Now once we simplified this equation, we can go ahead put the various form of y to simplify this. We have said that in general capital Y need not satisfy the differential equation given to us. Several useful approaches is depending on the what function we take. One of the first assumption is that suppose we assume that the y itself is a solution to our differential equation, then we get a certain simplification. That is the case which we first discussed. One of the important case is that when capital Y itself is one of the solution to the differential equation given to you. In such case, differential equation y for satisfied for the capital Y, that is a term exactly coming in the last term, which goes to 0, and then we get the simple form of a differential equation, that is capital V, that is a v double prime plus 2y prime by y plus p into v prime equal to 0. Now we see that this is basically a first order differential equation in v prime, and which we can solve using the techniques such as integrating factor, and then we can simply integrate it to obtain v. So this is now simply reduces to the first order differential equation, and we can basically solve. And this coefficient is already known to us because capital Y is already known and the P is also known, and in principle we can go ahead and solve this. So let's take an example. Let's look at the ordinary differential equation x minus 1 y double prime minus x y prime plus y is equal to 0. In this case, capital P is equal to minus x by x minus 1 and q is equal to 1 by x minus 1. Well, one of the solution to this differential equation is given by y is equal to e power x. How do we know that? Yes, it is given to you, so you don't really have to. But if you want to check, you can substitute this e power x. If you differentiate, you get e power x, and you can differentiate it again, you get e power x, and then you can differentiate it again and you get e power x, and you can go on doing that as many times. But in order to show that it is solution to this differential equation, it is sufficient to do it twice. Now we see that all the time x minus 1 and minus into 1 minus x comes out, and it does satisfies the differential equation. Once we know that, make a transformation of dependent variable, that is y is equal to v into e power x, and then we substitute in the differential equation. We have done all this exercise. We get x minus 1 into v double prime plus x minus 2 into v prime is equal to 0. Now we write w is equal to v prime, and then we get a differential equation in w, which is a first order linear differential equation, which can be solved using the integrating factor. What we have is w prime by w is equal to minus x minus 2 divided by x minus 1, which is equal to minus 1 plus 1 by x minus 1. In this case, it can simply be solved, and we have a d by dx of log w is equal to minus x plus log x minus 1. Once we solve this, what we get is a log w is equal to minus x plus log x minus 1. Once we have w, we can simply get v back by solving the differential equation. W is equal to v prime. Once we do that, it is easy to show that v is equal to x into e power minus x. So how do we check this? We can again substitute back in this differential equation and see whether y into e power x does satisfy this or not. The solution y is equal to e power x into v, that is equal to x, which would again satisfy the differential equation. So in this case, we have a two linearly independent solution, e power x and x. Are they linearly independent or not? You can figure it out by working out the Wronskian. There is another interesting form of second order ordinary differential equation, which is called the normal form of a ordinary differential equation. In this normal form, we basically try to get rid of the first order differentiation in the differential equation. That is, if we write the differential equation of the form d square y by dx square into v into y of x is equal to 0. In this differential equation, p of x, which comes as a coefficient of y prime, is equal to 0. So this is one form which we call a normal form of an ordinary differential equation. In the case of quantum mechanics, it comes as a Schrodinger equation with some potential v of x. That is why it is also very popular form in the physics. One may convert your ordinary differential equation into a normal form, and then it would look like a time independent Schrodinger equation. So this is why this is somewhat interesting. How to get it? It is basically cooking up the known form y of x, and then we set the first order term to 0. We have seen that when we do the substitution, small y of x is equal to capital V into capital Y. Then we substitute that. We have seen that it takes the following form. Once we have this, we set this to 0 and determine y with this differential equation, and then we have the differential equation in the normal form. Once we know y, we can determine y double prime and substitute in this term, and then that is what we get here, q of x in this term. So we set that to 0, then we get the differential equation y prime plus p by 2 into y is equal to 0, which we can substitute and get the solution. So we have one more homework problem here. We have an ordinary differential equation x minus 1 y double prime minus x into y prime plus y is equal to 0. Idea here is to bring this differential equation to the normal form. This is a homework problem, so you can upload the solution onto the vLearn. So it looks like we have had enough differential equation for a day, and let me stop here, and we will continue with the more of a differential equation, that is a second order ordinary differential equation, in the next lecture.